Hi everyone, I am Rishi Panchal. Welcome back to my channel. Today, we're diving into something truly groundbreaking in the semiconductor industry. While reviewing an ASML presentation, I noticed an interesting detail on one of their slides about the future of EUV lithography. ASML has been working on growing their power source to 800 watts or more, but how exactly they plan to achieve this wasn't entirely clear to me. Then I spotted something fascinating. They're planning to use 3 laser pulses instead of 2. This seemingly small change could revolutionize semiconductor manufacturing. In this video, I'll break down how EUV light sources work, why 3 pulses could be better than 2, and what this means for the future of chip manufacturing. Let's start with some basics. EUV, extreme ultraviolet light, has a wavelength of 13.5 nanometers, carrying about 92 electron volts of energy. To put this in perspective, your typical visible light photon has only between 1.5 and 3 electron volts. Producing such high-energy photons requires exciting atoms to higher energy states. When these atoms relax, they emit photons. The energy gap between these states needs to be around 92 electron volts, which is enormous. This requires highly ionized atoms, atoms stripped of several outer electrons. These inner electrons orbit much closer to the nucleus, feeling a stronger pull, allowing for higher energy transitions. Tin is the element of choice here. A neutral tin atom has 50 electrons. To produce EUV photons, we need tin ions missing 8 to 12 electrons. Creating this plasma of energized tin ions is the heart of EUV light generation. In a 2024 presentation, ASML introduced an equation for increasing oscillator that generated a seed laser pulse that could be amplified before hitting the droplet. This approach was called MOPA. MOPA worked, but conversion efficiency stayed below 1%. The spherical droplet was too dense. Light produced by the plasma was reabsorbed before reaching the collector. Other issues arose. Powerful lasers risked drilling through droplets, blasting them backward, or creating ultra-dense plasma that reflected energy away. Worst case, the laser's light could reflect back at the equipment itself, potentially causing massive damage. ASML and Cymer realized they needed to reshape the droplet before the main blast, so they added a pre-pulse to the MOPA system. This pre-pulse rapidly vaporizes material on the droplet's surface through ablation. The resulting pressure flattens and deforms the droplet into a disk, expanding it from 30 micrometers to 500 micrometers. This disk might be just nanometers thick at the center. A nanosecond later, the main pulse arrives, heating the disk and creating the EUV light plasma undefined. The first NXE30-100 MOPA plus pre-pulse systems arrived in 2013, demonstrating 50 watts, a massive improvement. By 2014, the NXE3300 added another power amplification round, pushing output to 80-100 watts. This breakthrough accelerated EUV adoption in manufacturing. So how do we scale up power further? Our options are somewhat limited. We can increase CO2 laser power on the droplet by improving the CO2 drive laser's efficiency, increasing droplet repetition rate. ASML has already pushed droplet frequency from 50,000 to 62,000 droplets per second and improved energy delivery, achieving about an 18% power increase. But there's a physical limit to how many droplets we can send through the chamber due to the plasma wind effect. When a droplet turns into plasma, it creates a small wind that can disrupt subsequent droplets. So our other lever is improving conversion efficiency, and this is where the 3-pulse approach comes in. The ASML slide I noticed showed 3 pulses in the new EUV sequence. The pre-pulse. This does what it always did, flattening and expanding the liquid tin droplet. The new rarefaction pulse. To rarefy means to reduce density. This pulse lowers the density of the tin disk, creating a pre-plasma plume of preheated tin atoms. The main pulse. The powerful CO2 pulse that produces the final plasma and EUV light. With just a solid disk, some of the main pulse's energy still reflects away, but the pre-plasma plume structure allows more tin atoms to absorb energy and emit EUV light, while allowing that light to escape with minimal reabsorption. This approach potentially increases conversion efficiency dramatically. The rarefaction pulse likely uses similar energy to the pre-pulse, but may be shorter to better ionize and preheat the material, undefined. Timing is absolutely crucial here. You can't hit the pre-plasma immediately after the second pulse. It needs time to disperse, but wait too long and it disperses too far, becoming too diffuse to generate sufficient EUV light. These timing windows are measured in microseconds. How might this be implemented? Patent applications suggest a sophisticated system with cameras measuring the size, position, and shape of thin droplets after each pulse. This information feeds back to computers controlling laser alignment in 3 dimensions. The system likely follows a 3-sequence startup procedure. First, the machine runs at low duty cycle with just the main pulse laser, calibrating positioning. Next, other lasers are added one by one, still at low duty cycle. Finally, all 3 lasers are fine-tuned for both hit rate and EUV output at high duty cycle, aiming to hit 80 to 90% of droplets. Conclusion. So, what does this all mean? Achieving a 3-pulse structure requires multiple precisely coordinated laser sources with nanosecond level timing precision and highly optimized pulse parameters. If ASML pulls this off, we could see a 30-50% jump in conversion efficiency and significantly reduced debris generation. Suddenly, 800 or even 1000 watts of EUV power becomes achievable. This is truly revolutionary. For years, EUV machines were photon-starved, limiting their applications. Now, we're looking at a future where photon scarcity could transform into abundance, opening exciting new possibilities for semiconductor manufacturing. Thanks for watching this deep dive into ASML's 3-pulse EUV technology. Drop your comments below about what you think this means for the future of chip manufacturing, and follow me for more such content on cutting-edge semiconductor technology.